So we are going to review Theorem 10.1 and then Theorem 10.2. Theorem 10.1 states, if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So that if L is a line that's tangent to circle Q at the point of tangency P, then L is perpendicular to the line segment QP. And we can see that in this example here. This is a picture of a circle. It has a center Q. It has a point of tangency P. QP is a radius, and L is the circle that is tangent to the circle, with P being the point of tangency. So what we need to prove is that QP is perpendicular to line L. So let us take a look at how we could go about proving that. Now in this picture here, we have a circle, and we have a line, and we have a radius that is drawn from the center of the circle to the point of tangency of the line. We need to prove that this radius is perpendicular to this tangent. So here we have labeled the center of the circle Q, and we've labeled the point of tangency P. So why is QP tangent to the line? Well, one thing we know is that a tangent has the property that it intersects a circle at only one point. So therefore, P is the only point at which the tangent intersects the circle. We can see from the diagram that for every other point on the line L other than P, we have the point outside the circle. It can't be inside the circle, because if it were inside the circle, it would intersect the circle in another point to emerge outside the circle. So every other point other than P is outside the circle. But we know that the radius, we don't know exactly what the radius is, but we know the length of the radius is QP. We also know that the length of any other distance from the center of the circle to the line, let's say from point Q to point R, which is on the line, is going to be a greater distance than the line of QP. That's because QR goes from the center of the circle to the circle and then beyond. So therefore it is greater than the magnitude of the radius. Since this is true for all points along line L, we therefore know that line segment QP of length radius has got to be the shortest distance from the point Q to the line L. We know from other more basic theorems in geometry that the shortest distance from a point to a line is the perpendicular from the point to the line. Therefore, we know that QP must be perpendicular to the line, so we can draw it as such. And that proves the theorem.